Right now, you're looking at a galaxy that died before Earth existed, and scientists have no idea how it happened. Max 21091 stopped forming stars over 10 billion years ago. It maintained its perfect spiral shape while becoming a cosmic corpse. According to every model we have, this should be impossible. But it's just one of thousands of galaxies breaking the rules we thought governed the universe. We're about to fly through structures so massive they challenge the laws of physics. You'll witness collisions that span hundreds of millions of years, discover rivers of superheated gas connecting every galaxy in existence, and see how half the matter in the universe was hiding in plain sight until 2018. But first, you need to understand something that will change how you see every star in the night sky. Until 2024, astronomers confidently stated there were 200 billion galaxies in our observable universe. That number already seemed incomprehensible. But when the James Webb Space Telescope pointed its infrared sensors at patches of space that appeared completely empty, it revealed something that forced us to rewrite every astronomy textbook. The real number? 2 trillion galaxies. For every galaxy we thought existed, 9 more were hiding in wavelengths our previous telescopes couldn't detect. Many are massive systems containing hundreds of billions of stars, completely invisible until Webb's instruments could see through cosmic dust and detect light that's been traveling for over 13 billion years. Think about this confirmed fact. In the time it takes you to read this sentence, light from thousands of these newly discovered galaxies has crossed another 1,000,000 miles on its journey toward Earth. Some of that light began traveling before our sun, ignited before the Milky Way formed its spiral arms, before the local group of galaxies even existed as a coherent structure. The Hubble Ultra Deep Field gave us our first hint. Astronomers pointed Hubble at a patch of sky smaller than a grain of sand held at arm's length, a region that appeared completely empty to every telescope that had observed it before. Over 11 days, Hubble collected 800 exposures of this apparent void. The result? 10,000 galaxies in that tiny slice of darkness. Each one represents an entire world. Billions of stars, trillions of planets, stellar nurseries where new suns are being born, supermassive black holes anchoring galactic centers, potentially countless civilizations we'll never contact or even know about. But here's where the scale becomes truly incomprehensible. That ultra-deep field represents just 1/13,000,000th of the entire sky. Multiply those 10,000 galaxies across the full sphere of space surrounding us, and the numbers spiral into territory where human intuition completely fails. 200 sextillion stars. That's a 2 followed by 23 zeros. More stars than grains of sand on every beach on Earth combined. And this is just within our observable universe, the bubble of space from which light has had time to reach us since the Big Bang. The actual universe extends far beyond what we can observe. Current measurements suggest space is geometrically flat, which means it's likely infinite. If true, then our 2 trillion observable galaxies represent an infinitesimally small fraction of everything that exists. Somewhere beyond our cosmic horizon, there are infinite copies of the Milky Way, infinite versions of Earth, infinite repetitions of this exact moment. But even within our observable bubble, we've only begun to understand what we're seeing. These 2 trillion galaxies aren't scattered randomly through space. They're organized into structures that dwarf individual galaxies the way galaxies dwarf solar systems. The Milky Way belongs to something called the local group, a gravitationally bound cluster of over 54 galaxies all performing an intricate cosmic dance. But the local group is just the beginning. We're part of something far larger, a structure so massive that light takes over 500 million years to cross from one end to the other. At the heart of this cosmic continent sits a gravitational monster that's pulling our entire galactic neighborhood toward it at over 1,000 miles per second. To understand where we're actually going, we need to zoom out from our galaxy and see our true cosmic address. Because when astronomers finally mapped the complete structure, we belong. In 2014, they discovered something that fundamentally changed our understanding of our place in the universe. The structure has a name, Laniakea, which means immeasurable heaven in Hawaiian, and it contains over 100,000 galaxies, all flowing like water toward a single point. But before we can explore this cosmic supercontinent, we need to understand the violent dynamics of our immediate neighborhood, where galaxies don't just orbit peacefully, they collide, they cannibalize, they die in ways that shouldn't be possible. Starting with our own galaxy's dark secret, the Milky Way is currently eating its neighbors alive. The Milky Way is a monster that's been devouring its neighbors for over 10 billion years. Right now, as you read this, our galaxy is violently tearing apart at least 2 smaller galaxies, consuming their stars one by one like a cosmic predator. The Sagittarius dwarf elliptical galaxy is being slowly shredded by our galaxy's gravitational field. Its stars are being ripped away and scattered into long streams that wrap around the Milky Way, like cosmic spaghetti stretching across hundreds of thousands of light years. Meanwhile, the Canis Major dwarf galaxy has been so thoroughly destroyed that astronomers only discovered its remains in 2003. This isn't a gentle merger. Think of it like a massive whirlpool encountering a fishing boat. The dwarf galaxy gets stretched and twisted by tidal forces that literally pull individual stars away from their home galaxy and fling them into the Milky Way's outer halo. Some of these stellar refugees will settle into stable orbits around our galactic center. Others get ejected entirely into the dark void between galaxies, doomed to drift alone through space for eternity. The evidence for this ongoing cannibalism is written in the stars themselves. Astronomers can identify which stars originally belonged to destroyed galaxies by studying their chemical composition and orbital patterns. Stars from the Sagittarius dwarf have a distinctly different mix of heavy elements compared to stars born in the Milky Way. It's cosmic forensics, solving crimes that happened billions of years ago. But the Sagittarius dwarf isn't going down without a fight. Its disruption is triggering waves of star formation throughout our galaxy's spiral arms. As the dwarf galaxy's gas clouds collide with material in the Milky Way's disk, they compress and heat up, creating stellar nurseries where new stars are born at an accelerated rate. The death of one galaxy feeds the birth of countless new stars in another. The large and small Magellanic Clouds are next on the menu. These 2 galaxies, visible from Earth's southern hemisphere, are currently about 160,000 light-years away. But they're not in stable orbits. Astronomers have confirmed both Magellanic Clouds are on a collision course with the Milky Way, expected to be fully consumed within the next 2 billion years. When the Large Magellanic Cloud finally merges with our galaxy, the event will be spectacular. The collision will trigger massive bursts of star formation that light up the night sky with brilliant nebulae. It could potentially wake up the supermassive black hole at our galaxy's center, turning it into a quasar that outshines entire galaxy clusters for millions of years. This galactic cannibalism isn't unique to the Milky Way. The Andromeda galaxy has been even more aggressive in consuming its neighbors. Astronomers have identified the remains of at least 10 different dwarf galaxies in Andromeda's outer regions. The evidence suggests it devoured most of them within the last few billion years. Some of these ancient meals are still visible as faint streams of stars stretched across hundreds of thousands of light years. The process follows a predictable pattern throughout the universe. Larger galaxies grow by consuming smaller ones, which in turn had previously consumed even smaller systems. It's a cosmic food chain that's been operating since the first galaxies formed over 13 billion years ago. Every major galaxy in the universe has a history written in the scattered remains of its victims. But this local cannibalism is nothing compared to what's coming next, because right now our entire galaxy is on a collision course with something far larger than any dwarf system we've consumed. In 4.5 billion years, the night sky will be on fire. The Andromeda galaxy, our nearest large neighbor, is racing toward us at 68 miles per second. At cosmic scales, it's like 2 freight trains barreling toward each other on the same track. The collision is inevitable, confirmed, and will completely reshape both galaxies in the most violent cosmic event our region of space has ever experienced. The Hubble Space Telescope settled the question definitively in 2012 by measuring Andromeda's sideways motion across the sky. For decades, astronomers knew the galaxy was approaching us, but they couldn't determine if it would be a direct hit or a near miss. Hubble's precise measurements revealed the terrifying truth. Andromeda is aimed directly at the Milky Way's heart. When galaxies collide, it's not like 2 solid objects smashing together. Galaxies are mostly empty space. The average distance between stars is about 25 trillion miles, so the chance of any two stars actually hitting each other during the merger is essentially zero. Instead, what happens is far more dramatic and chaotic. The collision will unfold over hundreds of millions of years, beginning with the outer edges of both galaxies starting to warp and stretch. Massive tidal forces will fling entire star systems out of their home galaxies and into the dark void between them. Some of these ejected stars will carry their planets with them, creating orphaned solar systems drifting forever through intergalactic space. As the two galactic centers draw closer, their supermassive black holes will begin a deadly spiral dance. The Milky Way's central black hole contains about 4 million times the mass of our Sun, while Andromeda's is significantly larger at roughly 100 million solar masses. When these monsters finally merge, they'll create gravitational waves so powerful they'll ripple through the fabric of space-time itself. The merger will trigger the most spectacular fireworks show in cosmic history. Gas clouds from both galaxies will collide and compress, igniting massive bursts of star formation that will light up the combined system like a cosmic Christmas tree. New stars will be born at a rate 10 times faster than what we see in either galaxy today. Earth's fate during this collision depends on cosmic luck. Computer simulations suggest there's roughly a 50% chance our solar system will be flung 3 times farther from the galactic center than we are now. There's also a 12% chance we'll be ejected from the merged galaxy entirely, sent wandering through the darkness between galaxy clusters. But there's essentially zero chance that any stars will physically strike our Sun or planets. If humanity still exists, when this collision begins, we'll have front row seats to watch it unfold over millions of generations. The night sky will gradually fill with new stars as Andromeda grows larger and brighter. Eventually, it will dominate the entire sky. The final product of this cosmic catastrophe will be a giant elliptical galaxy that astronomers have already nicknamed Milky Way. It will be roughly 10 times more massive than either original galaxy and will rank among the largest galaxies in our local supercluster. The elegant spiral arms of both galaxies will be destroyed, replaced by a smooth, featureless blob of stars. But even this ultimate collision pales in comparison to galaxies that have already died in ways that shouldn't be possible. Because scattered throughout the universe are cosmic corpses that challenge everything we thought we knew about how galaxies live and die. There are galaxies out there that have been dead for billions of years, and scientists have no idea how they died. Max 2129 looks like a perfectly normal spiral galaxy from a distance. It spins twice as fast as the Milky Way and contains several times more mass. But when astronomers looked closer, they discovered something that breaks every model of galaxy evolution we have. This galaxy stopped forming new stars over 10 billion years ago, making it a cosmic zombie that challenges everything we thought we knew about how galaxies live and die. Dead galaxies, or quenched galaxies as astronomers call them, are systems where star formation has completely shut down. In a normal galaxy like ours, massive clouds of gas and dust constantly collapse under their own gravity to birth new generations of stars. The process should continue for trillions of years until the universe itself expands so much that galaxies can no longer hold on to their gas supplies. But Max 2129 defied this natural order. Somehow, when the universe was less than a quarter of its current age, this galaxy exhausted or expelled all of its star-forming material. The problem is that according to our best models, this should be impossible for a galaxy of its size and type. Small galaxies can be quenched relatively easily. A nearby supernova explosion or the gravitational influence of a larger galaxy can strip away their gas supplies, effectively sterilizing them. But massive spiral galaxies like Max 2191 should have enough gravitational pull to hold onto their gas no matter what cosmic violence occurs around them. The discovery gets even stranger when you examine the galaxy's internal structure. Most dead galaxies that astronomers have found are elliptical-shaped, resembling cosmic footballs, with stars distributed roughly evenly throughout. These shapes make sense because they form when two spiral galaxies collide and merge, scrambling their organized structure. But Max 2129 maintained its spiral structure even as it died. The galaxy's stars are still arranged in elegant curved arms radiating out from a central bulge, exactly like a living spiral galaxy. It's like finding a perfectly preserved body that looks completely alive from the outside but contains no spark of life within. Even more puzzling, spectroscopic analysis reveals that the stars in this dead galaxy didn't form through the violent mergers that astronomers expected. Instead, they appear to have formed early in the galaxy's history through normal, peaceful star formation processes. Then something catastrophic happened that shut down all star formation almost instantly on cosmic timescales. Several theories attempt to explain this mystery, but none are fully satisfactory. One possibility is that the galaxy's central supermassive black hole went through an extremely active phase, generating powerful jets and radiation that heated up all the surrounding gas. This process, called AGN feedback, can be incredibly effective at suppressing star formation. Another theory suggests that the galaxy experienced a series of massive supernova explosions that collectively blew away its entire gas supply. But this would require an unprecedented level of coordination among stellar deaths, something that seems statistically unlikely. The most disturbing possibility is that we're missing something fundamental about how galaxies evolve. Max 21019-1 might represent a completely unknown process that can kill even the largest, most robust galaxies without warning. Perhaps there's a critical threshold where galaxies suddenly transition from active star formation to complete quenching, and we simply haven't identified. What triggers this phase transition? This dead galaxy isn't alone. Astronomers have now identified dozens of similar systems scattered throughout the distant universe. All are massive spiral galaxies that somehow died billions of years before they should have. Each discovery adds another piece to a cosmic puzzle that seems to grow more mysterious rather than clearer. But dead galaxies are just the beginning of the cosmic weirdness waiting in the depths of space. Because some galaxies aren't just dying quietly, they're being torn apart so violently that they look like jellyfish swimming through a sea of stars. ESO 27 Juri 001, located 220 million light-years away in the constellation Triangulum Australis, is caught in the act of being destroyed. The galaxy appears to be swimming through space, trailing long tentacles of gas and stars behind it like a cosmic jellyfish. But this isn't a peaceful swim through empty space. This galaxy is drowning. The destruction is caused by a process called RAM pressure stripping, and it's one of the most violent ways a galaxy can die. Imagine driving a convertible at highway speeds through a torrential downpour. The wind doesn't just get you wet, it strips the rain right off your windshield and flings it backward. Now scale that up to cosmic proportions. ESO 137 Z01 is racing through the Perseus galaxy cluster at over 1,000 miles per second. The space between galaxies in this cluster isn't empty. It's filled with extremely hot gas, heated to over 100 million degrees Fahrenheit. This gas is so thin that it would count as a perfect vacuum by Earth standards. But when you're moving through it at cosmic speeds, it becomes like hitting a brick wall. The RAMs, pressure from this hot intergalactic medium, is literally stripping away ESO 137-001's own gas supplies. The galaxy's outer layers are being peeled off like the skin of an onion, creating spectacular trails that stretch for over 200,000 light-years behind the galaxy. These trails contain enough material to form billions of new stars, but instead of fueling the galaxy's growth, this precious star-forming gas is being scattered into the void. What makes the imagery even more striking is that the stripped gas doesn't just disappear. As it gets torn away from the galaxy, it forms intricate structures that genuinely resemble the tentacles of a jellyfish. These tentacles are illuminated by ultraviolet radiation from young, hot stars that are still forming within the stripped material, creating an eerie blue glow against the darkness of space. The process is irreversible and ultimately fatal. Once a galaxy loses its gas supplies, it can no longer form new stars. The existing stars will continue to shine for billions of years, but gradually the galaxy will fade as its most massive stars burn out and explode as supernovae. Eventually, only dim red dwarf stars will remain, turning the once vibrant galaxy into a cosmic ghost. Astronomers have identified dozens of these jellyfish galaxies throughout nearby galaxy clusters, and each one tells the same tragic story. They're all caught in different stages of the stripping process, from galaxies just beginning to lose their outer gas layers to systems so thoroughly destroyed that only faint tentacles remain of what was once a thriving stellar metropolis. The Hubble Space Telescope has captured some of the most dramatic images of this destruction in action. In cluster after cluster, galaxies appear to be racing away from their own scattered remains. They leave trails of star formation in their wake like cosmic contrails. Some of these trails are so long and thin that they stretch across distances larger than our entire local group. But the violence doesn't stop with gas stripping. The same ram pressure that tears away a galaxy's star-forming material also disrupts its internal structure. Spiral arms get compressed and twisted, triggering bursts of star formation just before the gas supply is cut off forever. It's like watching a flower bloom just as it's being uprooted. The most haunting aspect of jellyfish galaxies is what they represent: cosmic beauty born from cosmic violence. These systems are among the most photogenic objects in the universe, with their streaming tentacles and bright blue star-forming regions creating images that belong in an art gallery. Yet each jellyfish galaxy represents the death throes of a system that might have harbored billions of worlds. There's a galaxy out there that shouldn't exist, and its very presence is breaking our understanding of how the universe works. NGC 1277 contains virtually no dark matter, which is like finding a skeleton without bones. Dark matter makes up roughly 85% of all matter in the universe and provides the invisible scaffolding that allows galaxies to form and maintain their structure. Without it, galaxies should either fly apart or never form in the first place. Yet NGC 1277 is sitting there in space, apparently held together by nothing but the gravity of its visible stars. This discovery sent shockwaves through the astronomical community when it was announced in 2018. For decades, the existence of dark matter has been considered one of the fundamental pillars of modern cosmology. We can't see it, we can't touch it, and we don't know what it's made of. But we know it's there because its gravitational effects are visible everywhere we look in the universe. Dark matter acts like invisible glue that holds galaxy clusters together. It's what allows spiral galaxies to spin without flying apart. It's what creates the cosmic web of filaments that connects all the large-scale structures in the universe. Without dark matter, the cosmos would look completely different if it could exist at all. NGC 1277 is what astronomers call a relic galaxy, meaning it formed early in cosmic history and has remained largely unchanged for billions of years. It's several times more massive than the Milky Way and packed into a much smaller volume, making it incredibly dense compared to modern galaxies. But despite containing hundreds of billions of stars, measurements show it has virtually no dark matter halo surrounding it. The initial discovery was controversial because it seemed to violate everything astronomers thought they knew about galaxy formation. Several teams of scientists double-checked the measurements, looked for errors in the data, and proposed alternative explanations. Maybe the galaxy was actually closer than originally thought, which would change the mass calculations. Maybe it had been somehow stripped of its dark matter by interactions with neighboring galaxies. But follow-up observations with multiple telescopes confirmed the impossible. NGC 1277 does appear to be a massive galaxy with little to no dark matter. The finding was so significant that it required scientists to seriously reconsider some of their most basic assumptions about how the universe works. One proposed explanation is that NGC 1277 formed through an extremely rare process where normal matter was somehow separated from dark matter during the galaxy's birth. This could happen if the galaxy formed from material that had been heated to such extreme temperatures that the dark matter and normal matter behaved differently, allowing them to separate. Another possibility is that the galaxy's dark matter was stripped away by gravitational interactions with the massive Perseus galaxy cluster where NGC 1277 resides. The cluster's enormous gravitational field might have been able to pull away the galaxy's dark matter halo while leaving the more tightly bound normal matter behind. But the most disturbing possibility is that our entire understanding of dark matter is fundamentally flawed. Maybe what we interpret as dark matter is actually a modification to the laws of gravity that behaves differently under certain conditions. If that's true, then NGC 1277 might be showing us what galaxies look like when this modified gravity effect is somehow turned off. The discovery has opened up new questions that astronomers are rushing to answer. Are there other galaxies like NGC 1277 hiding in the universe? Could entire regions of space exist where dark matter is absent? And what does this mean for our understanding of how structure formed in the early universe? What's certain is that NGC 1277 represents a cosmic anomaly that challenges everything we thought we knew about reality. There's a galaxy in the early universe where the gas clouds are shining brighter than all the stars combined, and scientists are calling it a totally new phenomenon. GSNDG 9422 exists from a time when the universe was only 1 billion years old, less than 10% of its current age. When astronomers first looked at its spectrum of light, they found something that had never been seen before: the signature of superheated gas that was actually outshining the galaxy's entire stellar population. In normal galaxies, stars are by far the brightest objects. They're nuclear fusion reactors that convert matter into energy at temperatures of millions of degrees, pumping out enormous amounts of light across all wavelengths. The gas between stars, while important for forming new stars, typically glows much more faintly and only shows up in specific narrow wavelengths. But GSNDG 9422 flips this relationship completely upside down. The galaxy's gas clouds are being heated to over 140,000 degrees Fahrenheit, nearly twice as hot as the surface of typical massive stars. At these extreme temperatures, the gas becomes so energetic that it outshines the very stars that are supposed to be heating it. The discovery came from the James Webb Space Telescope's infrared spectrograph, which can break down the light from distant galaxies into its component wavelengths like a cosmic prism. When lead researcher Alex Cameron first examined the data, his reaction was immediate. That's weird. It was exactly the kind of totally new phenomenon that Webb was designed to find in the early universe. The spectrum showed clear signatures of highly ionized gas, meaning the atoms in these clouds have been stripped of most of their electrons by intense radiation. This level of ionization requires an enormous input of energy, far more than what the galaxy's observed stars should be able to provide. Working with theorist Harley Katz, the team developed computer models to explain what could create such extreme conditions. Their conclusion suggests that GSNDG 9422 contains stars that are much hotter and more massive than anything we see in the local universe today. These primordial monsters might reach temperatures of over 140,000 degrees Fahrenheit at their surfaces, making them incredibly efficient at pumping out ultraviolet radiation. The implications extend far beyond just one weird galaxy. This gas outshining phenomenon might represent a missing link in our understanding of how the universe evolved from its dark ages into the star-filled cosmos we see today. During the first few 100 million years after the Big Bang, the universe was filled with neutral hydrogen gas that blocked most light from traveling very far. Something had to ionize all that hydrogen to make the universe transparent. Astronomers have long suspected it was the first generation of stars, but regular stars don't seem capable of producing enough ultraviolet radiation to do the job. Galaxies like GSNDG 9422, with their superheated gas and ultramassive stars, might be showing us exactly how cosmic ionization actually happened. The discovery also suggests that the early universe was a much more violent and energetic place than previously thought. If galaxies could heat their gas to these extreme temperatures, it means star formation in the early cosmos was far more intense and chaotic than what we see in modern galaxies. But perhaps most intriguingly, this type of gas-dominated galaxy might help explain how the very first stars formed in the universe. These population 3 stars have never been directly observed but are predicted to have been hundreds of times more massive than our Sun. They likely lived very brief, violent lives. GSNDG 9422 provides the first observational evidence that such extreme stellar populations might have actually existed. But even this weird early galaxy seems almost normal compared to the massive systems that somehow assembled impossibly early in cosmic history. The James Webb Space Telescope has found galaxies that are so massive and formed so early that they're breaking our models of how the universe should work. 3 galaxies, nicknamed the Red Monsters, contain as much mass as our entire Milky Way, but they existed when the universe was less than 1 billion years old. That's like finding a fully grown adult at a preschool. According to our best theories of galaxy formation, these massive systems shouldn't have had enough time to assemble so early in cosmic history. The red monsters get their name from their distinctive appearance in Webb's infrared images. They glow with a deep red color because they're packed with dust, which absorbs blue and ultraviolet light from their stars and re-emits it as infrared radiation. This dust content is itself another mystery because dust grains form from heavy elements produced inside stars over multiple generations. How did these early galaxies accumulate so much dust so quickly? Galaxy formation in the early universe was supposed to be a gradual process. According to the Standard Model, small clumps of dark matter slowly grew larger through gravitational attraction, eventually becoming massive enough to trap gas and begin forming stars. This process should take billions of years to create galaxies as large as the Milky Way. But the red monsters appear to have compressed this entire evolutionary sequence into less than 1 billion years. They're forming new stars at nearly twice the rate of similar mass galaxies today, suggesting that star formation in the early universe was far more efficient than our models predict. The discovery came from the FRESCO survey, which uses Webb's near-infrared camera combined with a GRISM spectrograph to measure precise distances and masses of early galaxies. Out of hundreds of galaxies studied, these 3 red monsters stood out as clear outliers that demanded explanation. What makes the finding even more puzzling is that these massive galaxies seem to be converting a much higher percentage of their available gas into stars than should be possible. In normal galaxy formation, supernova explosions and radiation pressure from massive stars blow away most of the gas that could potentially form stars. This feedback mechanism prevents galaxies from becoming too massive too quickly. But somehow the red monsters overcame this natural limitation. They managed to hold on to their gas supplies and convert them into stars with unprecedented efficiency. It's like finding a factory that operates at 200% capacity, without any of the usual problems that should shut it down. The implications extend beyond just these 3 galaxies. If massive galaxies could form this efficiently in the early universe, it suggests that the cosmic environment 1 billion years after the Big Bang was fundamentally different from what we see today. Maybe the intergalactic medium was denser, making it easier for galaxies to accrete material. Maybe supernova feedback was less effective at early times. Or maybe our understanding of dark matter and galaxy formation is missing crucial pieces. The red monsters might be telling us that there are physical processes operating in the early universe that we haven't discovered yet. Each red monster contains roughly 300 billion stars, comparable to the total stellar mass of the Milky Way. But they're packed into much smaller volumes, making them incredibly dense compared to modern galaxies. Their central regions probably contain stellar densities thousands of times higher than what we see in our galactic neighborhood. The discovery of the red monsters represents what researchers are calling a too many, too massive problem. Not only did these individual galaxies grow larger than expected, but there are too many of them scattered throughout the early universe. Our models predict that such massive early galaxies should be extremely rare, yet Webb is finding them everywhere it looks. We are looking at the most distant object ever discovered by humanity, and it existed when the universe was only 280 million years old. The galaxy designated JD's GSZ140 represents the ultimate time machine, showing us conditions when our cosmos was barely 2% of its current age. The light reaching us today from this cosmic infant began its journey over 13.5 billion years ago, when the first stars were just beginning to illuminate a universe that had been dark for hundreds of millions of years. JD's GS018 shattered the previous distance record by revealing a galaxy from an era we'd never observed before. That might not sound dramatic, but in the context of the early universe, pushing back even 20 million years represents a significant fraction of the total time that had elapsed since the Big Bang. The galaxy's discovery required pushing the James Webb Space Telescope to its absolute limits. Even with Webb's unprecedented infrared sensitivity, JD's GSZ140 appears as just a few pixels of reddish light against the cosmic background. But those pixels contain information that has traveled farther through space and time than any signal humanity has ever detected. The extreme distance means we're seeing JD's GSZ140 at a redshift of z equals 14.32. Redshift measures how much the expansion of the universe has stretched the wavelengths of light during its journey to us. A redshift of 14.32 means the galaxy's light has been stretched by a factor of over 15, moving even its ultraviolet emissions into the infrared wavelengths where only Webb can detect them. What makes Jade's GS Z14-0 even more remarkable is that it's not just distant, it's also surprisingly massive and bright for such an early galaxy. The system contains several 100 million times the mass of our Sun, all packed into a region spanning roughly 1,600 light-years across. That's incredibly compact compared to modern galaxies, suggesting that star formation in the early universe was much more concentrated and intense. The galaxy appears to be in the midst of a furious burst of star formation, creating new suns at a rate that would build the equivalent of our entire solar system every few years. This level of activity produces so much ultraviolet radiation that it ionizes the surrounding gas, creating a bubble of transparency in what was otherwise an opaque universe. The discovery came through the JADE survey, which uses Webb's spectrograph to confirm whether candidate early galaxies are really as distant as they appear, or are actually nearby imposters reddened by dust. Spectroscopic analysis confirmed JADE's GS Z14-0's extreme distance and revealed that the galaxy contains surprisingly heavy elements for such an early system. The presence of oxygen and other metals indicates that multiple generations of massive stars had already lived and died. By the time we're seeing this galaxy, star formation must have begun even earlier than we thought possible. The first stars must have formed within the first 100 to 200 million years after the Big Bang, compressing an enormous amount of cosmic evolution into a remarkably short time span. The galaxy's existence raises profound questions about how structure formed in the early universe. Current models predict that it should have taken longer for dark matter halos to grow massive enough to host such bright galaxies. JADE's GS Z14-0 suggests either that galaxy formation was more efficient than we realize, or that the early universe contained physical processes we haven't yet discovered. Perhaps most mind-boggling is the realization that we're seeing JADE's GS Z14-0 as it appeared when the universe was still emerging from its cosmic dark ages. This was an era when most of space was filled with neutral hydrogen gas that blocked light from traveling very far. The galaxy we're observing existed at the very beginning of cosmic rionization, when the first stars began clearing away this primordial fog. But JADE's GS Z14-0 is just one member of a growing population of early galaxies that are rewriting the story of cosmic dawn. Every photon of light from these primordial galaxies is a time traveler that began its journey when the universe looked nothing like it does today. The epoch between 200 million and 1 billion years after the Big Bang represents the most dramatic transformation in cosmic history. This era, called Cosmic Dawn, witnessed the birth of the first stars, the formation of the first galaxies, and the complete restructuring of all the matter in the universe from a dark neutral fog into the transparent star-filled cosmos we see today. Before Cosmic Dawn, the universe was literally dark. No stars existed to produce light. The cosmic microwave background radiation had cooled below visible wavelengths, leaving space filled with nothing but invisible neutral hydrogen gas and mysterious dark matter. If you could somehow travel back to this time, you wouldn't be able to see your hand in front of your face, no matter how powerful your flashlight. But hidden within this darkness, gravity was slowly assembling the first structures. Tiny variations in the density of dark matter, imprinted during cosmic inflation just after the Big Bang, grew larger over millions of years. These dark matter halos eventually became massive enough to trap the surrounding hydrogen gas, creating the raw material for the first stars. The very first generation of stars, known as Population 3 stars, were unlike anything that exists today. With no heavy elements available except what was created during Big Bang nucleosynthesis, these primordial giants formed from pure hydrogen and helium. Computer models suggest they were monsters containing hundreds of times more mass than our Sun and burning at temperatures hot enough to synthesize the first carbon, oxygen, and iron in the universe. These stellar behemoths lived fast and died young, exploding as hypernovae after just a few million years. Their deaths seeded the surrounding space with heavy elements, allowing the second generation of stars to form with more diverse chemistry. It was this second generation that began assembling into the first true galaxies. The James Webb Space Telescope is giving us our first direct glimpses of cosmic dawn by detecting galaxies from this crucial epoch. Each discovery is like finding a fossil from the early universe, preserving conditions that existed over 13 billion years ago. These galaxies are so distant that we're literally seeing them as they were when the universe was still a cosmic infant. What's emerging from Webb's observations is a picture of cosmic dawn that's far more violent and chaotic than astronomers expected. The early galaxies are more massive, more active, and more numerous than our models predicted. Star formation rates in these systems are off the charts, suggesting that the first billion years of cosmic history were characterized by incredibly rapid and efficient galaxy assembly. The light from these primordial galaxies also carries information about the process of cosmic reionization. As the first stars began pumping out ultraviolet radiation, they gradually ionized all the neutral hydrogen in the universe, making space transparent for the first time since the cosmic microwave background was released 380,000 years after the Big Bang. This reionization process wasn't uniform. It began around the most massive early galaxies and slowly spread outward, creating bubbles of ionized gas that eventually merged to encompass the entire universe. Webb can actually map this process by studying how the light from distant galaxies is absorbed by intervening neutral hydrogen. Each new galaxy discovered from cosmic dawn adds another piece to this puzzle. We're learning that the transition from darkness to light happened faster and more dramatically than anyone imagined. The universe went from being completely dark to hosting massive bright galaxies in less than 1 billion years, a cosmic transformation that ranks among the most important events in the history of everything. But these individual early galaxies were just the beginning of much larger cosmic violence that would reshape entire regions of space. Two galaxies have been locked in a cosmic death spiral for over 600 million years, and we're watching the final act of their violent ballet. The antennae galaxies, officially designated NGC 4038 and NGC 4039, are located 68 million light-years away in the constellation Corvus. They earned their nickname from the spectacular tidal tails that stretch out from their distorted cores like the antennae of some cosmic insect. But these aren't gentle appendages, they're streams of stars, gas, and dark matter being violently torn from their parent galaxies by gravitational forces that dwarf anything we can imagine. This collision began around 600 million years ago when the two spiral galaxies first began to feel each other's gravitational influence. At that time, both were probably beautiful, well-ordered spiral systems similar to our own Milky Way. But as they drew closer together, their mutual gravity started to distort their shapes, pulling stars and gas into long streamers that now stretch over 200,000 light-years into space. The violence of this encounter is difficult to comprehend. Each galaxy contains hundreds of billions of stars, and all of them are being gradually accelerated and flung around by gravitational forces millions of times stronger than anything our solar system experiences. Some stars are being ejected entirely from both galaxies, destined to wander alone through intergalactic space for billions of years. But the most spectacular part of this cosmic collision is the burst of star formation it has triggered. When gas clouds from the two galaxies collide, they compress and heat up, creating ideal conditions for new stars to form. The antennae system is currently giving birth to new stars at a rate roughly 10 times higher than what we see in normal galaxies. These stellar nurseries are visible as brilliant blue and pink regions scattered throughout the collision zone. The blue areas mark clusters of hot young stars that are pumping out enormous amounts of ultraviolet radiation. The pink regions show where this ultraviolet light is hitting surrounding gas clouds, causing them to glow like cosmic neon signs. The Hubble Space Telescope has revealed that the antennae collision is creating some of the most massive star clusters ever observed. These stellar metropolises contain millions of stars packed into regions just a few dozen light-years across. If Earth were located near one of these superclusters, our night sky would be filled with thousands of stars brighter than Venus. Computer simulations show that the antennae galaxies are still approaching their moment of maximum violence. Over the next few 100 million years, their cores will spiral closer together, triggering even more intense bursts of star formation. Eventually, the two central supermassive black holes will merge in an event that will send gravitational waves rippling across the universe. The final product of this collision will be a single giant elliptical galaxy, larger and more massive than either of the original spirals. Most of the gas that currently fuels star formation will either be converted into new stars during the merger or blown away by supernova explosions, leaving behind a relatively quiet red system dominated by older stars. This transformation from spiral to elliptical is one of the fundamental processes that has shaped galaxy evolution throughout cosmic history. The antennae represent this process caught in the act, allowing astronomers to study exactly how galactic mergers unfold over hundreds of millions of years. What makes the antennae particularly valuable for research is that they're close enough for us to resolve individual star-forming regions and study the merger process in incredible detail. Astronomers can track how star formation rates change in different parts of the collision zone, measure the properties of newly formed star clusters, and even detect individual supernova explosions within the chaos. But individual galaxy collisions, like the antennae, are just small-scale versions of much larger cosmic violence that plays out in galaxy clusters. In the richest galaxy clusters, smaller galaxies are being systematically tortured and destroyed by their more massive neighbors in a process astronomers call galactic harassment. The Coma cluster, located 320 million light-years away, contains over 1,000 galaxies packed into a region roughly 20 million light-years across. It sounds spacious, but at cosmic scales, this represents an incredibly dense concentration of massive objects, all moving at tremendous speeds through a shared gravitational environment. The result is cosmic chaos on an unimaginable scale. Galactic. Harassment occurs when galaxies experience repeated high-speed encounters with their neighbors over billions of years. Unlike the slow, intimate mergers we see between pairs of galaxies, harassment involves brief but violent gravitational interactions that gradually tear apart smaller systems without fully destroying them in a single encounter. Imagine a small galaxy as a carefully constructed sandcastle, and the cluster environment as a beach during a hurricane. Each wave that hits the castle doesn't completely destroy it, but gradually erodes its structure, carrying away sand grain by grain until nothing recognizable remains. This is exactly what happens to galaxies in rich clusters, except the waves are gravitational forces from passing neighbors. The process is particularly devastating for spiral galaxies like our own Milky Way. Their delicate spiral arms and extended gas disks are easily disrupted by tidal forces from larger galaxies. During each harassment encounter, streams of stars get stripped away from the spiral arms, while ram pressure from hot intergalactic gas removes the cold gas needed for future star formation. The Hubble Space Telescope has captured dramatic images of harassment in action throughout the Coma cluster. Galaxies appear distorted and stretched, with long tails of stars trailing behind them like cosmic contrails. Some systems are so thoroughly disrupted that they barely resemble galaxies at all, appearing more like shapeless clouds of stars scattered across hundreds of thousands of light-years. One of the most striking examples is a galaxy designated NGC 4676, nicknamed the Mice because of its distinctive double-tail structure. This system started as two separate spiral galaxies that experienced a close encounter about 160 million years ago. The gravitational interaction stretched both galaxies into long, narrow shapes, resembling the tails of mice, hence the nickname. But the mice represent just one moment in an ongoing process of destruction. Computer simulations show that these tidal tails will eventually be stripped away entirely, leaving behind two small, compact elliptical galaxies that will barely resemble their original spiral forms. The stars scattered in the tails will either be ejected into intergalactic space or eventually fall back to join one of the surviving galactic cores. The violence isn't limited to interactions between galaxies. The cluster environment itself is hostile to galaxy survival. The space between galaxies in rich clusters is filled with hot, tenuous gas heated to temperatures of over 100 million degrees Fahrenheit. This intergalactic medium acts like a cosmic wind that strips away the cooler gas that galaxies need for star formation. The combined effect of harassment and gas stripping transforms the galaxy population in clusters over cosmic time. Rich clusters today are dominated by large elliptical galaxies. and small gas pore systems called dwarf ellipticals. Very few large spiral galaxies survive in these environments, and those that do are usually found in the outer regions where the harassment is less intense. This cosmic violence has been operating for billions of years, fundamentally reshaping the galaxy population throughout the universe. Computer models suggest that most of the dwarf elliptical galaxies we see today in clusters are actually the remnants of larger spiral systems that were harassed into submission over cosmic time. But the destruction visible in galaxy clusters is just the tip of the iceberg compared to the invisible architecture that shapes everything we can see in the universe. Everything you can see in the universe is built on a foundation of something completely invisible. Dark matter makes up 85% of all matter in existence. Yet it interacts with nothing except gravity. It doesn't emit light, it doesn't absorb light, and it doesn't reflect light. It's essentially the ghost of the cosmos, detectable only through its gravitational fingerprints on everything else. But without this invisible scaffolding, none of the galaxies we've been exploring could exist. Think of dark matter as the skeleton that gives shape to the cosmic body. Just as your bones provide the framework that allows your muscles and organs to maintain their structure, dark matter provides the gravitational framework that allows normal matter to clump together into stars, galaxies, and larger structures. Without it, the universe would be a smooth, featureless soup of gas with no structure at all. The evidence for dark matter is overwhelming and comes from multiple independent sources. When astronomers measure how fast stars orbit around galaxy centers, they find that the outer stars are moving much too quickly to be held in place by the gravity of visible matter alone. The galaxies should fly apart, yet they don't. Something invisible must be providing the extra gravitational pull needed to keep them intact. Galaxy clusters provide even more dramatic evidence. When the Coma cluster was first studied in 1933, astronomer Fritz Zwicky calculated that the galaxies within it were moving so fast that the cluster should have dispersed billions of years ago. The only explanation was that the cluster contained far more mass than could be seen, hidden in some invisible form that Zwicky called dark matter. Modern techniques have allowed astronomers to actually map the distribution of dark matter throughout the universe using gravitational lensing. Massive concentrations of dark matter bend and distort the light from background galaxies, creating a cosmic funhouse mirror effect that reveals where the invisible matter is located. These maps show that dark matter forms a vast web-like structure spanning billions of light years. The cosmic web consists of dark matter filaments connecting massive nodes where galaxy clusters reside. Between these filaments lie enormous voids where very little matter of any kind exists. This web-like pattern provides the underlying architecture that determined where galaxies would form and how they would be distributed throughout space. On smaller scales, every galaxy sits at the center of a dark matter halo that extends far beyond the visible stars. Our own Milky Way is embedded within a dark matter halo that stretches at least 600,000 light-years from the galactic center, 3 times larger than the visible galaxy itself. This halo contains roughly 10 times more mass than all the stars and gas in the galaxy combined. Computer simulations show that without dark matter, the universe would look completely different. The tiny density fluctuations that existed just after the Big Bang would never have grown large enough to form the first stars and galaxies. The cosmic microwave background would still show the same small temperature variations we observe today, but they would never have evolved into the rich tapestry of cosmic structure we see around us. Yet despite decades of searching, scientists still have no idea what dark matter actually is. It could be composed of exotic subatomic particles that interact only through gravity. It could be primordial black holes left over from the early universe, or it could be something even stranger that we haven't imagined yet. What we do know is that this invisible foundation shapes absolutely everything else in the cosmos. But some regions of space contain dark matter structures so massive they harbor no visible light at all. Hidden throughout the universe are massive dark matter structures that contain no stars, no gas, and no light whatsoever. These dark galaxies represent some of the most mysterious objects in existence. They have enough mass to qualify as galaxies, containing billions of times the mass of our sun, but they emit no light across any wavelength of the electromagnetic spectrum. They're essentially invisible cities of dark matter floating through the cosmic void. detectable only through their gravitational effects on nearby objects. The existence of dark galaxies was first predicted by computer simulations of cosmic structure formation. These models showed that while most dark matter halos should capture enough normal matter to form visible galaxies, some halos should remain dark, either because they formed in regions with very little gas or because some process prevented normal matter from falling into them. Finding these invisible objects requires detective work on a cosmic scale. Astronomers look for their gravitational signatures by studying how they bend and distort light from background galaxies. When a dark galaxy passes between us and a more distant light source, its gravity acts like an invisible lens, creating telltale distortions that reveal its presence. One of the most compelling candidates for a dark galaxy is a massive structure discovered through gravitational lensing in the direction of the Virgo cluster. This invisible object contains roughly 1 billion times the mass of our Sun, but produces no detectable light at any wavelength. It's like finding a city-sized building that casts a shadow but is completely invisible to every form of detection except its gravitational influence. The mystery deepens when you consider what could keep such massive dark matter halos from forming stars. In normal galaxy formation, dark matter halos capture surrounding gas through gravitational attraction. This gas cools and condenses into clouds that eventually collapse to form the first stars. Once star formation begins, the process becomes self-sustaining as new generations of stars continue to form from recycled material. Several theories attempt to explain how dark galaxies could avoid this fate. One possibility is that they formed in regions where the intergalactic gas was too hot to be captured by the dark matter halo's gravity. High-energy radiation from nearby galaxies or black holes could have heated the surrounding medium to temperatures where gas atoms move too quickly to be gravitationally bound. Another theory suggests that dark galaxies represent failed attempts at galaxy formation. Perhaps these halos began capturing gas and forming stars, but some catastrophic event stripped away all their normal matter before the process could be completed. Interactions with larger galaxies or passage through galaxy clusters could potentially remove all visible matter while leaving the dark matter halo intact. The most intriguing possibility is that dark galaxies represent a completely different evolutionary pathway that we don't yet understand. Maybe there are physical processes operating in certain environments that actively prevent normal matter from clustering within dark matter halos, creating these ghostly structures as a natural consequence of cosmic evolution. Recent observations with the James Webb Space Telescope are beginning to shed light on this mystery by detecting extremely faint galaxies that previous telescopes missed entirely. Some objects that were classified as dark galaxy candidates are turning out to be ultra-faint dwarf galaxies with just enough star formation to be barely detectable in infrared light. But other candidates remain completely dark despite Webb's unprecedented sensitivity. These confirmed dark galaxies challenge our understanding of the relationship between dark matter and normal matter in the universe. They suggest that galaxy formation is more complex and varied than our current models predict. The existence of dark galaxies also has profound implications for our census of cosmic structure. If significant numbers of galaxy-mass dark matter halos remain invisible, then we're dramatically underestimating the total amount of structure in the universe. What makes this even more mind-bending is realizing that these dark galaxies exist within an even larger invisible framework that connects every visible structure in the cosmos. Your cosmic address is far stranger and more vast than you could ever imagine. Most people know they live on Earth, in the solar system, in the Milky Way galaxy, but that's like saying you live in a house without mentioning the city, state, or continent. Your full cosmic address includes the local group, the Virgo cluster, and ultimately the Laniakea supercluster, a gravitationally connected structure containing over 100,000 galaxies spread across 520 million light-years. Laniakea wasn't discovered until 2014, which means humanity only recently learned the true scale of our cosmic neighborhood. The name means immeasurable heaven in Hawaiian, and it's a fitting description for a structure so vast that light takes over 500 million years to cross from one end to the other. The discovery came from mapping the peculiar motions of galaxies throughout our region of space. While the expansion of the universe carries most galaxies away from each other, Gravity also creates additional motions as galaxies are pulled toward massive concentrations of matter. By measuring these peculiar velocities, astronomers could trace the gravitational flows that define supercluster boundaries. What they found was astounding. The Milky Way, Andromeda, and tens of thousands of other galaxies are all flowing like water toward a massive gravitational attractor at the center of Laniakea. This great attractor region contains the mass of tens of thousands of galaxies and is pulling our entire cosmic neighborhood toward it at over 1,000 miles per second. But Laniakea itself is flowing toward an even larger structure called the Shapley Attractor, located roughly 700 million light-years away. This creates a cosmic river of galaxies all streaming in the same direction across distances that dwarf our previous conception of large-scale structure. The Virgo cluster sits near the center of Laniakea and serves as the dominant gravitational influence in our cosmic region. This cluster contains over 2,000 galaxies, including several giant ellipticals that rank among the most massive galaxies in the known universe. The cluster's total mass is roughly 1,000 trillion times that of our Sun, making it one of the nearest examples of truly large-scale cosmic structure. Our local group, containing the Milky Way, Andromeda, and over 50 smaller galaxies, occupies a relatively quiet region on the outskirts of Laniakea. We're located in what astronomers call a cosmic suburb, far from the violent cluster environments where galaxy collisions and harassment are common. This peaceful location may have been crucial for allowing complex life to evolve on Earth. The structure of Laniakea reveals the cosmic web in action. Massive filaments of dark matter and galaxies connect the major galaxy clusters, while vast voids separate different regions of the supercluster. Our local group sits on one of these filaments, connected to the larger cosmic architecture but isolated enough to avoid the destructive processes that occur in denser environments. What's truly mind-bending is realizing that Laniakea represents just one node in an even larger network of superclusters stretching across billions of light-years. The Perseus-Pisces supercluster, the Hydra-Centaurus supercluster, and dozens of other massive structures create a cosmic web pattern that extends to the limits of our observable universe. Recent surveys have revealed that these superclusters aren't randomly distributed. They appear to be organized into even larger structures called galaxy filaments and walls, some of which stretch for billions of light-years across space. The largest of these structures challenge our understanding of how the universe evolved from the smooth conditions observed in the cosmic microwave background. The discovery of Laniakea fundamentally changed our perspective on humanity's place in the cosmic hierarchy. We're not just residents of a galaxy or even a galaxy group. We're citizens of a vast cosmic continent containing 100,000 galaxies, all connected by the invisible threads of gravity into a single coherent structure. Yet even this immense supercluster is just one small section of something far more vast and interconnected. The universe is built like a cosmic spiderweb, with massive filaments of dark matter and galaxies stretching across distances so vast they make entire superclusters look like tiny decorations. These galaxy filaments are the largest known structures in the universe, commonly reaching 50 to 80 megaparsecs in length. That translates to roughly 160 to 260 million light-years, distances so enormous that light from one end of a typical filament takes longer to reach the other end than complex life has existed on Earth. But some filaments are true cosmic monsters. The largest confirmed structure is called the Hercules Corona Borealis Great Wall, stretching over 10 billion light-years across space. That's roughly 1/10 the diameter of our entire observable universe. If you could somehow travel at the speed of light, it would take you 10 billion years just to cross from one end of this structure to the other. These filaments form the backbone of cosmic architecture, connecting galaxy clusters and superclusters in a vast three-dimensional web that spans the entire universe. The pattern resembles a neural network or the internal structure of a living cell, with dense nodes connected by elongated strands and vast empty spaces between them. The cosmic web emerged from tiny quantum fluctuations that existed just after the Big Bang. During cosmic inflation, these microscopic variations in density were stretched to astronomical scales. Over billions of years, gravity amplified these small differences, causing matter to flow along the paths of least resistance between the densest regions. Dark matter led this cosmic construction project. Because it interacts only through gravity, dark matter could begin clustering as soon as the universe became cool enough for stable structures to form. Normal matter followed the dark matter's gravitational lead, flowing along the same pathways to create the galaxy filaments we observe today. The space between galaxies within these filaments isn't empty. It's filled with the warm, hot intergalactic medium, a tenuous gas heated to temperatures between 100,000 and 10 million degrees Fahrenheit. This gas is so thin that it barely qualifies as matter by Earth standards, but there's so much of it spread across such vast volumes that it contains more normal matter than all the stars in all the galaxies combined. Detecting these cosmic filaments requires sophisticated techniques because they're among the faintest structures in the universe. The gas within them is too thin and hot to emit much visible light, and the dark matter is completely invisible. Astronomers find them by mapping the distribution of galaxies and using computer simulations to trace the underlying dark matter web. One of the most successful detection methods uses gravitational lensing on massive scales. The combined gravitational field of dark matter within a filament can bend light from background galaxies, creating subtle distortions that reveal the filament's presence. Recent surveys have used this technique to map filaments connecting galaxy clusters across billions of light years. The cosmic web profoundly influences galaxy evolution. Galaxies located within filaments have access to a steady supply of fresh gas flowing along the dark matter streams. This gas fuels ongoing star formation, allowing filament galaxies to remain active and continue growing for billions of years longer than galaxies in other environments. Conversely, galaxies that end up in the spaces between filaments, called cosmic voids, gradually exhaust their gas supplies and fade into old red systems dominated by dying stars. The cosmic web literally determines which galaxies thrive and which ones wither away over cosmic time. The largest filaments contain thousands of galaxy groups and clusters, all flowing along the same cosmic highways. The local group containing our Milky Way sits on a relatively minor filament connecting the Virgo cluster to more distant structures. But even this modest cosmic strand spans tens of millions of light years and influences the motion of every galaxy within it. Some structures in the universe are so mind-breakingly large that they shouldn't exist according to our models of cosmic evolution. The Sloan Great Wall stretches over 1.3 billion light years across space, making it one of the largest known structures in the universe. To put this in perspective, if our entire observable universe were reduced to the size of Earth, the Sloan Great Wall would be roughly the size of North America. It contains tens of thousands of galaxies arranged in a sheet-like configuration that challenges our understanding of how structure could form on such enormous scales. But the Sloan Great Wall pales in comparison to the Hercules Corona Borealis Great Wall, a structure so massive that some astronomers question whether it can actually exist within our current cosmological models. This cosmic behemoth spans over 10 billion light years, making it roughly 1/10 the size of the entire observable universe. These great walls represent the largest density enhancements in the cosmic web, regions where multiple galaxy filaments converge to create sheet-like structures containing millions of galaxies. They form the boundaries between vast cosmic voids like the walls of enormous soap bubbles floating in space. The discovery of these massive structures came as a shock to cosmologists because they approach or exceed the theoretical maximum size that structures should be able to reach in our universe. According to the cosmological principle, matter should be distributed roughly uniformly on the largest scales. Structures like the Hercules Corona Borealis Great Wall test the limits of this fundamental assumption. The problem stems from how long it takes for gravity to build such massive structures. Even at the speed of light, it would take 10 billion years for gravitational influences to cross from one end of the Hercules Corona Borealis Great Wall to the other. Since the universe is only 13.8 billion years old, there shouldn't have been enough time for gravity to coordinate the formation of structure on such enormous scales. Yet these cosmic walls clearly exist, forcing astronomers to reconsider some of their basic assumptions about cosmic evolution. One possibility is that the early universe contained much stronger density fluctuations than we currently believe, providing larger seeds for structure formation. Another theory suggests that exotic physics during cosmic inflation could have created preferred directions in space, leading to enhanced structure formation along certain axes. The Great Walls also provide crucial insights into the nature of dark energy, the mysterious force driving the accelerated expansion of the universe. The existence of such large structures places constraints on how dark energy behaves, because too much dark energy would prevent large-scale structure formation entirely. Galaxy surveys continue to discover new examples of these massive walls throughout the observable universe. The CFA-2 Great Wall, discovered in 1989, was the first structure recognized to span hundreds of millions of light-years. The Boss Great Wall, found in 2016, stretches over 1 billion light-years and contains some of the most distant galaxies ever observed. Each discovery adds to our understanding of the cosmic web's largest components. These walls aren't solid barriers, but rather enhanced regions of the web where galaxy filaments cluster together. They contain billions of galaxies connected by dark matter filaments and separated by regions of cosmic void. The internal structure of great walls reveals the hierarchical nature of cosmic architecture. Within each wall, galaxies are organized into smaller groups and clusters, which in turn are connected by filaments spanning tens of millions of light-years. It's like zooming into a fractal pattern where each level of magnification reveals similar organizational structures. Living within the cosmic web means that our entire observable universe represents just a small section of potentially infinite structure extending in all directions. The great walls we can observe might be just the local examples of patterns that repeat throughout an infinitely large cosmos. What makes this even more profound is the realization that these massive structures exist within ocean-like regions where almost nothing exists at all. Between the massive filaments and great walls lie regions of space so empty that they make the vacuum between stars look crowded by comparison. Cosmic voids are the largest empty spaces in the universe, spanning hundreds of millions of light-years with almost no galaxies, stars, or even dark matter within them. These regions are so devoid of matter that if Earth were located in the center of a typical void, we wouldn't have discovered that other galaxies exist until the 1960s, and we'd still know about fewer than a dozen of them today. The Buddha's void, also called the Great Nothing, exemplifies the extreme emptiness of these cosmic deserts. This spherical region spans roughly 330 million light-years in diameter but contains almost no galaxies in its interior. If the Milky Way had formed in the center of the Biota's void, the nearest galaxy would be over 150 million light-years away, making it invisible to all but our most powerful telescopes. To understand just how empty these voids are, consider that the average density of matter throughout the universe is roughly 6 hydrogen atoms per cubic meter. That's already incredibly sparse by everyday standards, but within cosmic voids, the density drops to less than 1/10 of this universal average, creating regions that are emptier than the best vacuums we can create in laboratories on Earth. These voids didn't form through some cosmic explosion that cleared out the matter. Instead, they represent regions where the initial density of matter after the Big Bang was slightly lower than average. While gravity was pulling matter together to form filaments and galaxy clusters, these underdense regions became even emptier as their sparse matter was gravitationally attracted to the denser region surrounding them. The process is still continuing today. Computer simulations show that cosmic voids are gradually expanding as the universe ages. Matter continues to flow out of these regions toward the surrounding walls and filaments, making the voids progressively larger and emptier over cosmic time. Eventually, voids will merge together to create even more enormous empty regions. The few galaxies that do exist within cosmic voids are strange objects that challenge our understanding of galaxy formation. These void galaxies tend to be small, blue, and actively forming stars, characteristics that are unusual for galaxies in such isolated environments. They should have exhausted their gas supplies billions of years ago, yet many continue producing new stars at surprisingly high rates. One explanation is that void galaxies represent a different evolutionary pathway. Without the harassment and ram pressure stripping that affects galaxies in denser environments, void galaxies may be able to hold onto their gas supplies much longer than their counterparts in filaments and clusters. The largest known void is the giant void in the constellation Eridanus, spanning roughly 1 billion light-years across. This cosmic desert is so large that it contains several smaller voids within it, creating a hierarchical structure of emptiness that mirrors the hierarchical clustering of matter in the cosmic web. Living in a cosmic void would provide a profoundly different perspective on the universe. Instead of seeing thousands of galaxies scattered across the night sky, you'd see perhaps a handful of faint smudges representing the most massive galaxy clusters on the void's boundary. The universe would appear far more empty and desolate than the rich tapestry of stars and galaxies visible from our location within the cosmic web. Voids also play a crucial role in cosmic evolution by providing space for the universe to expand. As dark energy accelerates the expansion of space, voids grow larger while the matter-filled regions become relatively more compressed. This process will continue for trillions of years, eventually creating a universe dominated by enormous empty regions separated by thin filaments containing all the remaining matter. But even these vast empty regions exist within a universe where matter and energy are locked in constant warfare on every scale imaginable. Right now, 4 massive galaxy clusters are colliding in the most violent event our universe has witnessed since the Big Bang itself. The collision is taking place in galaxy cluster MAX J0717, located 5.4 billion light-years away. Each of the 4 clusters contains hundreds of galaxies and trillions of stars, plus enormous quantities of hot gas and dark matter. When objects this massive collide, they release more energy than the explosion of billions of supernovae happening simultaneously. This cosmic pileup represents the ultimate expression of gravitational violence in the modern universe. The clusters are approaching each other at speeds of thousands of miles per second, their mutual gravity accelerating quadrillions of tons of matter toward an inevitable rendezvous that will reshape an entire region of space. The Chandra X-ray Observatory has captured stunning images of this collision in progress, revealing the hot gas within each cluster glowing at temperatures of over 100 million degrees Fahrenheit. As the clusters merge, their gas clouds collide and compress, heating the material to even more extreme temperatures and creating shockwaves that propagate outward for millions of light years. But the most fascinating aspect of this collision is how it separates different types of matter through the violence of the impact. The hot gas in each cluster experiences friction and turbulence during the collision, causing it to slow down and lag behind. But the galaxies themselves, being much denser and more compact, pass through the collision zone with relatively little interaction. This creates a situation where the galaxies in each cluster become separated from their own hot gas, like runners leaving behind their shadows during a race. The dark matter in each cluster behaves similarly to the galaxies, feeling only gravitational forces and passing through the collision with minimal interaction. Gravitational lensing observations reveal the dark matter distribution during these cosmic crashes, showing how the invisible scaffolding of the universe responds to extreme gravitational stress. The dark matter halos of the colliding clusters stretch and distort as they interact, creating tidal forces that can strip away smaller satellite galaxies and fling them into intergalactic space. The energy released during major cluster collisions is so enormous that it heats the intergalactic medium across hundreds of millions of light years. This heating can suppress galaxy formation throughout entire regions of space by making it impossible for gas to cool and condense into new stars. Some cluster collisions create even more exotic phenomena. When 2 clusters with roughly equal masses collide head-on, they can pass through each other completely and then be pulled back together by their mutual gravity for a second collision. This process can repeat multiple times, creating a cosmic ping-pong effect that lasts for billions of years. The Bullet Cluster represents one of the most studied examples of this type of collision. 2 galaxy clusters collided at such high speed that their hot gas was completely separated from their galaxies in dark matter. The resulting configuration provided some of the strongest evidence for dark matter's existence, since gravitational lensing showed that most of the mass in the system was located with the galaxies rather than the hot gas. Computer simulations of cluster collisions reveal the incredible complexity of these events. The process unfolds over hundreds of millions of years, with multiple phases of approach, collision, separation, and re-collision. Each phase triggers different types of physical processes, from shock heating of gas to tidal stripping of galaxies to the formation of massive radio-emitting structures. The violence of cluster collisions also triggers intense bursts of star formation as gas clouds within galaxies are compressed by shock waves. Some of the most luminous galaxies in the universe are found in colliding clusters, powered by star formation rates hundreds of times higher than what we see in isolated galaxies. But the violence visible in these collisions is just part of a larger cosmic ecosystem where matter flows between structures in ways that were hidden from our view until very recently. After flying through 2 trillion galaxies across 13.8 billion years of cosmic history, we return to the most profound question of all. What does this mean for us? Every galaxy we've explored, from the most distant cosmic dawn infant to the massive present-day giants, formed through the same fundamental processes that created our own Milky Way. The carbon in your body was forged in the nuclear furnaces of massive stars that exploded billions of years ago. The oxygen you breathe came from stellar death throes that seeded space with heavy elements. You are literally made of star stuff that has been recycling through the cosmic web for eons. But the cosmic perspective reveals something even more profound. In a universe containing 2 trillion galaxies, each harboring hundreds of billions of stars and potentially trillions of planets, the mathematical certainty is overwhelming that we are not alone. The same physical and chemical processes that led to life on Earth must be occurring on countless worlds throughout the cosmos. Yet despite this statistical certainty of cosmic companionship, we remain practically alone in our observable universe. The distances between stars and galaxies are so vast that meaningful communication or contact with other civilizations may be forever impossible. We are simultaneously part of an infinite cosmic community and isolated on our small blue world. This paradox defines the human condition in the 21st century. We've discovered our true place in a universe far grander and more violent than our ancestors could have imagined. We've learned that Earth orbits an ordinary star in the outer reaches of a typical galaxy that's just one member of a modest galaxy group in an unremarkable region of a vast supercluster, which itself is merely one node in an infinite cosmic web. From this perspective, every human conflict, every political boundary, every economic system seems almost absurdly small. Wars fought over patches of land on a single planet pale in significance compared to galaxy collisions that reshape entire regions of space over hundreds of millions of years. The rise and fall of civilizations becomes a brief flicker in a cosmic timeline that stretches from the Big Bang to the heat death of the universe, trillions of years in the future. Yet the cosmic perspective also reveals the extraordinary preciousness of what we have here on Earth. In a universe dominated by radiation, plasma, dark matter, and the violent extremes of stellar nucleosynthesis, planets capable of supporting complex chemistry and life are rare cosmic treasures. Earth represents billions of years of cosmic evolution concentrated into a single world where the universe became conscious of itself. We are the universe's way of knowing itself. Through human consciousness, the cosmos has developed the ability to contemplate its own existence, to trace its history from the first moments after the Big Bang to the present, and to predict its future evolution across unimaginable spans of time. Every telescope observation, every scientific discovery, every moment of cosmic wonder represents the universe looking at itself through our eyes. This realization carries profound responsibility. We are the only known beings capable of preserving and transmitting cosmic knowledge across generations. The story of the universe, from quantum fluctuations during cosmic inflation to the formation of 2 trillion galaxies, exists in its full glory only within human consciousness and the scientific records we create. Our cosmic journey through every galaxy in the observable universe reveals that we live in an age of unprecedented discovery. Never before in human history have we been able to see so far into space and time, to understand so much about our cosmic origins and destiny, or to appreciate the true scale of the universe we inhabit. The James Webb Space Telescope and future observatories will continue pushing back the frontiers of knowledge, revealing new types of galaxies, new cosmic phenomena, and deeper insights into the fundamental nature of reality. Each discovery adds another piece to the cosmic puzzle, bringing us closer to answering the ultimate questions about existence and purpose. Perhaps the most important lesson from our journey through 2 trillion galaxies is that the universe is far stranger, more beautiful, and more awe-inspiring than we ever imagined. From dark matter scaffolding to galactic cannibalism, from impossible early galaxies to cosmic web filaments spanning billions of light years, reality consistently exceeds the limits of human imagination. We end where we began, as temporary arrangements of atoms in an infinite cosmos, but now with the knowledge that we are participants in the most extraordinary story ever told. The evolution of the universe itself, from simplicity to complexity, from darkness to light, from unconscious matter to conscious beings capable of contemplating their own cosmic significance.